Hello students, so in this lecture we will do the numerical techniques based upon method of false position. Now in the previous lecture of lecture number 258 we have discussed about the bisection method. Now this bisection method, although it finds the roots, it is comparatively slow method. That is the problem with this method, and we need to speed up. Now to speed up, we require this another method that is called this false position method, or in Latin it is called regula falsi. Now how to start this? We will start in the same way as we start the bisection method. Uh, Suppose we need to find the root of an equation, root of a number t. So we will assign a function fx is equal to x square minus t, and we will locate 2 points x0 and x1 such that fx0 and fx1 they have opposite signs. Here's the first step. After that, the next step will be to connect these 2 points. Means we have fx0 and fx1. Connection in a straight line will take place. So connect these 2 points and then find it where it is cutting the x-axis. Find where this connecting line is meeting the x-axis. Now it meets the x-axis at the point x2. So we will find fx2 and see that whether if fx2 and fx0 are of if they are of the opposite sign, and then if this is the case, then we will replace x1 by x2, and if they are of the same sign, then we will replace x0 by x2. So in both these cases, as in the bisection method, the new interval is smaller than the previous one, and they ultimately they will converge to the root when we will keep on doing this. Now to get an equation to find the successive approximation in the root, we need to formulate an equation. So what we will do, so graphically if we see what is actually happening, you say we have a function like this. Okay. So as in the previous case, we have assigned 2 points. One say is this point, this is x0, and one is say this point, this is x1. Now at this point we are getting fx0, and at this point we are getting fx1. So in the bisection method we were finding out an point here, and which is the bisection of this x0 and x1, and then we were finding the value of the function at this point. Instead of doing this, what we are doing here, we are connecting these 2 points, connecting this f0 with this f1 with a straight line, and we are finding out this point, which is, we are calling it as x2. So what this and then we are finding out the value of fx2 here. So what this procedure is doing, it may be similar to the bisection method, but it is saving a lot of time. So saving a lot of iterations, so that we are approaching the convergence at a much faster rate. So let's formulate the formula, and one important thing is that after we are finding out the value of x2, we are seeing whether it is matching with whether it has we are comparing the signs, and then what we are doing, if this has got a slope, so we are actually allowing the slope to move further close to the original uh, polynomial, so that we can get the error is reduced. So to find the slope, we need to formulate the equation. So the slope after connecting the points fx1 and fx0, we have connected the point and we want to find the slope. So the slope is simply fx1 minus fx0 divided by x1 minus x0, and this is the slope, this is the tan theta, and this is again is equal to fx1 divided by x1 minus x2, considering the fact that now the line has the connecting line has got the x-axis, so we can write x1 minus x2 as equal to fx1 by tan theta, and that is again equal to fx1 into now use this take this one and put it here. So it becomes into x1 minus x0 divided by fx1 minus fx0, and from this equation we ultimately get the value of x2 is equal to x0 fx1 minus x1 fx0 divided by fx1 minus fx0. So this is the formula that we require for x2. Now if you look into the algorithm part, the algorithm part has two new features. Compared to the bisection method. The first one is we have a limit to the total number of iterations to n. We limit the total number of iterations to n. And then the second one is that the convergence is checked by checking the value of fx. Convergence is checked by checking the value of fx if it is close to 0. If this is the case, then we can say that x is the root. So these two new features have been added to the algorithm which were not present in the algorithm for the bisection method. Now checking the value of fx is acceptable provided the slope of fx near the specified root is not too small. So this is acceptable provided the fx is acceptable provided the slope of fx is not too small. So if the slope is too small, then there can be a large error in the root even the fx may be small. So this condition has to be satisfied. That means we are talking about a condition where this is the case. There has to be some slope. Okay, so this is the root, and this is fx, and this is x. This is the root. So let's write the algorithm. So we will first start with assigning the different values. That we will read the initial two approximations x0, x1, then e and n. These are the initial two guesses. This is the error and this is the number of iterations we have assigned. So then we will see whether sine of fx 0, it is if it is not sine of fx1, the two signs should be equal. And so then we shall assign f0 as fx0 and f1 as fx1, and then we will start the iteration. That means for 1 to n we will use the formula just we derived. We will say that x2 is equal to x0 f1 minus x1 f0 divided by f1 minus f0, and then we will assign f2 to fx2, and then we will see whether if this value of f2 is less than the precision value, then we will write this is a convergent solution. That means now the fx is equal to 0 and the solution is x2 and f2. So if x2 is the root, stop. However, if the sign however if sine of f2 is not equal to the sine of f0, then we'll assign x 0 to x1, and sorry, this will be f2, and f1 to f2. Else, if the signs are equal, then we will have x2 replacing x0 and f2 replacing f0. So then we will write end for, then stop and end. So that's how the program stops. So if we take an example, say you have been asked to find the value of the root of 25 as in the previous case. So the function is now x square minus 25. So we will take the initial guess x0 as 2 and x1 as 7, and f0 corresponding to x0 is minus 21, and f1 corresponding to x1 is 24, so the value of x2 is x0 f1 minus x1 f0 divided by f1 minus f0. So if we put the values, it comes out to be 2 into minus 21 minus 7 into 24, and it's 24 plus 21. So do the calculations. This is equal to 2 into, oh sorry, so it will be 24 plus 21, and then it will be x0 is 2 and f1 is 24 minus x1 is 7 and f1 is minus 21, so it will be 48 plus 147 divided by 45. So it will be again 148 plus 147 divided by 45. So if we go to so 48 plus 147 divided by 45, it gives you the value 4.34. So it's 4.34. No, it's, we know that the exact value is 5, but it is close to the value. So we'll calculate fx2 now, that is the function of f x squared minus 25. So that will be so the value of x2 is 4.34. Calculate fx2, it is 4.34 whole square minus 25. So it is obviously not equal to 0, and the sign is negative, whereas the sign of f1 was 24 and f0 was minus 21. So these two are having the same sign. So these two are having the same sign, we need to replace x2 by x0 by x2 and do the same calculations between x1 and x0, that is between 7 and 4.3. So the range, what has happened is, now we know that the range is, initially we were trying to find out the solution between 2 and 7. So by doing this, initially we were trying to find out the answer between 2 and 7. Now we are trying to find the answer between 4.34 and 7. So this is now becoming the x2, and this is now x1. Okay, so we know that the answer is 5, so it will keep on this is the E error, and this will keep on reducing until we get to a value which is very close to 5. So in that case, fx2 will be also very close to 0. So that's where we will get the solution.